let's go for next level of formulation of Lagrangian. So today we will just try to formulate Lagrangian. But before that, what we have to do? We have to learn little bit about calculus of variation, because Lagrangian formulation is based on Hamilton's principle, and Hamilton's principle is just a mathematical uh, part of mathematical application of calculus of variation. So let's try to see what is calculus of variation, and we will just try to solve one problem based on also calculus of variation, and after that we will formulate basically principle of least action, which is popularly known as Hamilton's principle. So let's go for calculus of variation. So what we have, suppose we have any integral, and this integral is equal to some function f, and which is function of y dot, and x dx. And what is y dot? Y dot is nothing but it is defined as dy upon dx. So I have defined that my integral I is equivalent to some function f, which is function of y dot, and x dx. Suppose this integral is extremum, then the first derivative di must be equal to 0, which means that d, the first derivative of integral f y dot x dx must be equal to 0. Extremum means we can talk about minima or maxima, both can be possible. So first derivative must be equal to 0. And if this condition hold, then if di is equal to 0, then this f will follow, f which is function of y dot x will follow Euler-Lagrange's equation. Euler-Lagrange's equation. And what is this Euler-Lagrange's equation? The Euler-Lagrange's equation is d upon dx del f upon del y dot minus del f upon del y must be equal to 0. So this is very famous mathematical equation. This is known as Euler-Lagrange's equation. And once you follow this all particular concept, then you can easily find the maxima and minima of any particular function. And this is one of the mathematical tools, which is not a part of our syllabus actually. But yes, we have to learn this thing because it is very useful to formulate the Lagrangian. So let us try to use this particular concept of calculus of variation. This is just a full concept, a full definition of calculus of variation. I am not going to further derivation because it's not a part of our syllabus. But we will try to use one particular problem and we will try to see how we can apply this thing. Then we will go for actual thing that is known as what? Hamilton's principle. So obviously, we know that suppose we have y versus x and we have point A and point B. So what will be the shortest distance between point A and point B? This is a straight line, isn't it? We know this fact and we will just try to prove this fact. Okay. So shortest distance, so we know that shortest distance in a plane is identified as a straight line. We know this fact and we will try to learn this thing with help of this calculus of variation. So what I am going to do, I am just going to take one particular arbitrary path from A to B, and let's say this path is S. This is my arbitrary path. I can just take some small element, and this small element of path is ds. So I am just keeping this thing zoomed for you. So this part is something like known as ds, the small element. So what is this ds? This ds can be written as this value is nothing but dx, and this value is nothing but dy. Hence ds tends to 0. Hence ds tends to 0. We can assume this can be something like a straight line. So because ds tends to 0, this is all about calculus, nothing else. So what we are going to do, we can write ds is equal to root under dx square plus dy square. Okay. And if we are going to integrate whole ds, then we have this path, isn't it? We have this particular path. So how we can write all this thing? Let's go for the real thing of this particular thing. So I am just going to remove this part. So what we have, s is nothing but integral of ds, and which is nothing. I can write this value as something dx square plus dy square. I can write this value as integral of 1 plus dy upon dx whole square, and I can take ds as a common. So this is nothing but integral of ds, and which will be s. And what we want? We want this s have to be extremum. I just want that this s must be extremum. That means the first derivative of this particular integral must be equal to 0. This is all about condition of extremum. Then if this condition hold, then what is my f? This is my f. You remember from the last, just we have written that this is my f. Then what will happen? This particular f, this function will follow Lagrange's equation, Euler-Lagrange's equation. This function f will follow Euler-Lagrange's equation. So what will happen to this equation? I can write df, sorry, d upon dx del f upon del y dot del f upon del y must be equal to 0. And what is my f? I can identify my f. This value is nothing 1 plus y dot square. This is my f. Now what will value of del f upon del y? Del f upon del y is 0, because this is not a function of y, but this is function of y dot. So del f upon del y is 0. We can also calculate del f upon del y dot. What will be this value? When we are going to calculate it, first I have to go for root part, then y dot part, and then when we will go for differentiate y dot, then 2.5 will be cancel out. So I think we will get this value y dot root under 1 plus y dot square. Everyone is comfortable up to this?
Yes, sir.
Yes, sir.
Okay. So now this value have to satisfy this equation. This all thing we are just going to calculate it. So when we are going to calculate it, then we have d upon dx del f upon del y dot is nothing but y dot root under 1 plus y dot square minus del f upon del y 0 is equal to 0. So what will happen? This value is some constant, isn't it? This value is constant because d upon ddx is equal to this value of the first differentiation is equal to 0, that means I can claim y dot root under 1 plus y dot square is equal to some constant alpha. Now, what I will do, I will take it here, make it square both sides, then I can have y dot square must be equal to alpha square 1 plus y dot square. Okay, so I will just take y dot together, y dot square together, then we have basically this particular equation. We have y dot square 1 minus alpha square is equal to alpha square. This is constant. So y dot is equal to alpha upon root under 1 minus alpha square. So this is some constant value, isn't it? Constant by some constant, 1 minus alpha square is also constant. So I can say this value is m. Now, what is y dot? Y dot is nothing but dy upon dx, and that value is m. And when we are going to solve this differential equation, then obviously y is equal to mx plus some integral constant that will depend on initial condition. And you can just see that this value is nothing but the equation of a straight line. So we have proved that the shortest distance between the 2 points in a plane is nothing but a straight line. So this is very important mathematical tool to get the shortest distance, shortest path, optimum distance. Lot of questions can be done onto this basis, but this is not a part of our syllabus actually in a direct way, but we have to use this thing. How we have to use this thing? That will be the basic mathematical philosophy of classical mechanics, that is known as Hamilton's principle, that is basically principle of least action. So let's go for principle of least action. Before that, if you have any doubt, you can raise the question.
So ये left hand पे last step जो है उसके बाद क्या है?
Sorry, left hand पे this value.
Last equation, last.
This value. Y is equal to mx plus c. C is some constant when you will do the differential equation.
This step written at the end.
Huh?
Y dot square equals alpha square.
This one.
Last. बिल्कुल last. Sir.
This one.
हाँ, इसके बाद क्या किया सर?
इसके बाद क्या किया? Y dot को एक साथ ले लिया, y dot स्क्वायर को. So 1 minus alpha square is equal to alpha square.
Okay sir.
है ना? उसको just वेरिएबल सेपरेबल कर रहे हैं बेसिकली, है ना? ओके, और कुछ पूछना है
सर?
हाँ,
प्रिंसिपल ऑफ लीस्ट एक्शन एंड हैमिल्टन्स प्रिंसिपल इज सेम.
यस एग्जैक्टली, अभी उसी के बारे में बात करेंगे. एग्जैक्टली,
ठीक है.
ओके, सो अप टू दिस एवरीवन इज कंफर्टेबल? ओके, चलो देखते हैं. लेट्स स्टार्ट फॉर्मुलेशन ऑफ क्लासिकल मैकेनिक्स. सो अभी तक हम जो भी कर रहे थे, दे आर द प्री रिक्विजिट ऑफ क्लासिकल मैकेनिक्स. क्लासिकल मैकेनिक्स शुरू करने के पहले हमें इतनी बातें जरूर ध्यान में रखनी चाहिए, एंड देन वी कैन स्टार्ट विद द बेसिक फिलॉसफी ऑफ क्लासिकल मैकेनिक्स. दिस इज द मोस्ट इंपॉर्टेंट थिंग, एंड लेट्स ट्राई टू फिगर इट आउट. व्हाट इज दिस? हियर वी आर टॉकिंग अबाउट Hamilton's principle. Hamilton's principle. And this is also identified as principle of least action. Okay. So this is Hamilton's principle, and we are just talking about principle of least action. Let's try to go for this. Now, there is a very philosophical question is there, and obviously, suppose this is one particular mass, and if I am throwing this mass in a vertical position, and I assume that there is always, we are just doing this experiment again and again. We are throwing in a vertical direction, and it will come to my hand. You can see this will come to my hand. If my initial condition is same, all the environment is also same, then obviously we have precise trajectory of this particular particle. Same way, if I will throw this particle with some angle, then obviously it will make projectile. There is precise nature of a particle. Precise nature of a path. Now, what is the real question? The real question is very philosophical. Suppose we are talking about some y versus t. Let's say we are just talking about some y versus t. And here is my initial position, and here is my final position. Then we can have infinite number of path possible, that such that we can go from 1 to 2. We can go from this path. Somebody can go from this path. Somebody can go from this path. Somebody can go from this path. Please, initial condition and environment are same. All forces what is acting is same at every point of time. So we can have mathematically infinite number of path. But is that my particle is following infinite number of path?
No,
Is that it is possible into classical mechanics that your particle will
Yes.
follow infinite number of path?
Yes, sir.
No, it cannot be possible. अगर ऐसा हो पाता, then what will be real problem? Look at suppose some t is equal to t. You can have at this some particular time t is, let's say this time is t naught. You can आप यहां भी हो सकते हो, यहां भी हो सकते हो, यहां भी हो सकते हो, यहां भी हो सकते हो. Is that it is possible?
क्वांटम बिहेवियर है सर ये तो.
Obviously, this is not possible. Quantum behavior है या नहीं है, that is different issue. But in general, if I will throw this particle, then obviously it will follow the same trajectory again and again. It is not possible that at the same time you are here also, you are here also, you are here also, you are here also. अगर ऐसा हो जाए तो फिर क्या बात है? मैं एक साथ कई क्लासरूम में पढ़ा सकता हूं, isn't it?
Yes, sir.
ऐसा हो सकता है क्या? Never.
No, sir.
या फिर आप भी एक साथ कई क्लासरूम में पढ़ सकते हैं, है ना? So this is not possible. So which path will particle follow? Which path is going to followed by particle? So it is a very serious question, and we have to give this answer. Then Hamilton's come into picture, and he defined one very interesting term that is known as action. So he defined the term action. What is action? Action, let's say action is defined as A, and which is given by some function. Action is some function of generalized coordinate, generalized velocity, and it may be function of time and dt. So he defined a term which is known as action. Action is nothing but function of generalized coordinate, generalized velocity, and time dt. This is definition of action. So what is Hamilton's principle or principle of least action? He stated a particle will follow only those precise path precise path for which action of a system, and this action is A, this action of a system is extremum. What is the meaning of that? Meaning of that, particle will follow that path for which del variation of A, or you can say del variation of L dt must be equal to 0. So particle will not follow every path. He will follow those paths for which the del variation is equal to 0. Now we can compare it with the calculus of variation. What is calculus of variation? The calculus of variation is del variation of f function of y dot x dx. This must be 0. And here the principle of least action will tell you del variation of L generalized coordinate. L is the function of generalized coordinate, generalized velocity, and time dt. Now what we can do? We can compare these two things. So f can be compared to L, y can be compared to qi, y dot can be compared to qi dot, and x can be compared to t. Now, if this f is going to follow Euler-Lagrange's equation, then this L have to also follow Euler-Lagrange's equation. So what will be Euler-Lagrange's equation for this particular L? So let us try to write the Euler-Lagrange's equation for this particular L. So Euler-Lagrange's equation for this particular L is known as d upon dt del L upon del qi dot minus del L upon del qi is equal to 0. And this famous equation is identified as Lagrange's equation of motion. This famous equation is identified as Lagrange's equation of motion. So this is one of the famous equation. Now, hence it is equation of motion. That means this must be equivalent to Newton's law, isn't it? This must be equivalent to Newton's law. So we have to construct L. We have to define L such that this equation must be behave like a Newton's law. Newton's law, millisecond law, F is equal to ma. Then we identify this particular L, and this particular L is identified as function of generalized coordinate, generalized velocity, and time, and this is identified as nothing but kinetic energy minus potential energy of a system. So we identify L, and this L is nothing but the kinetic energy and potential energy of a system. And finally, and this is identified as very famous formulation that is known as Lagrangian of a system. So yes, we formulate Lagrangian of a system on the basis of principle of least action and calculus of variation. And this action A is defined as L dt, which is very much something like where L can be finally identified as T minus V, kinetic energy minus potential energy of a system.
So how we
this
identify
is all about action. Yes.
So how
Clear?
we identify that the function L
Sorry.
So how we identified that this function L is t minus v?
Because I want this thing as a f is equal to ma. We tried different types of formulation, but finally it suited that if L is t minus v, so you can write it in this way, that if L is equal to t minus v, then this is equivalent to Newton's law. So actually we want equation of motion. We want equation of motion. So why we have defined L is nothing but kinetic energy minus potential energy of a system.
Okay, sir.
Okay. So now this is all about basic formulation of Lagrangian. So look at how Lagrangian come into picture. And once you have this Lagrangian on the basis of principle of least action, where we have defined action, and this action is just a mathematical thing, nothing to do with the physical thing. Every quantity cannot be physical, because t minus v, what is t minus v? Can you identify t minus v? You can have T plus V as the total energy of a system, but T minus V is not any physical quantity. Is that any physical quantity?
No, sir.
No. But yes, we have defined T minus V such that we can define the action of a system, that is L dt. And finally, from there, we can reach the Newton's law of motion. So ultimate aim is that we have to reach Newton's law of motion, because that is only equation of motion, isn't it? We have to see how my state is evolving with the time, and that can be only explained by the Newton's law of motion. So this is one of the very fundamental principle. This is principle. Okay, this is principle, mathematical principle, I can say in a very modest language, because I didn't read anything about the physical meaning of action. We have just used it as a mathematics, but finally we reach the physics, which is F is equal to ma. So this is one of the very fundamental thing. If you want to add something on this, you are welcome.
Sir, how we know this condition is F is equation of motion?
Because I want this should be equation of motion. Are you getting my point?
ठीक है.
We want this should behave like equation of motion. So why we have to write the suitable expression of L. Okay. And that this T minus V will fit in a very nice way. Okay. So now we have Lagrangian, we have Lagrange's equation of motion. Now we have to construct more physical quantity from this particular Lagrangian and Lagrange's equation of motion. Okay. So let's try to go for this. Okay. So what we have Lagrangian of a system, and which is function of generalized coordinate, generalized velocity, and time. This is my Lagrangian of a system. So Lagrangian of a system, and this is equivalent to, this should be function of generalized coordinate, generalized velocity, and the time. So these are conjugate one. You can have more than one generalized coordinate and you can have more than one generalized velocity. And this is nothing but identified as kinetic energy minus potential energy of a system. And what is Lagrange's equation of motion? Lagrange's equation of motion is given by d upon dt del L upon del qi dot minus del L upon del qi must be equal to 0. And this is known as Lagrange's equation of motion. And finally, this will equivalent to sum f is equal to ma. You will see when we will try to solve different types of problem. Now let's go for next definition. The next definition is generalized momentum. Okay, so this is generalized momentum. So if qi is generalized coordinate, if qi is generalized coordinate, then generalized momentum corresponds to qi is pi. Okay, qi is pi, where pi is defined as del L upon del qi dot. This pi is defined as del L upon del qi dot. What is qi dot? Qi dot is nothing but generalized velocity. So we have relationship between generalized velocity and momentum. Your generalized momentum can be linear momentum, can be angular momentum, depends on what is your dimension of generalized coordinate. So if your generalized coordinate is linear, obviously associate momentum is linear in nature. If your generalized coordinate is angular, then obviously associate momentum is angular in nature. So we have generalized momentum in this particular concept. Okay. Now, but the most important thing is all about cyclic coordinate. Cyclic coordinate. So you can have more than one generalized coordinate. So if I have Lagrangian, and this Lagrangian can be function of generalized coordinate, and let's say it is function of q1, q2 up to let's say qn, and this Lagrangian has also function of q1 dot, q2 dot, and you have qk dot also, as well as you can just go for qn dot. Suppose this is the form of Lagrangian, and if you are just going to check whether this Lagrangian is, so I'm just going to write here. So suppose I have Lagrangian in this form, and for generalized coordinate qk, for generalized coordinate qk, if del L upon del qk is equal to 0, that means that is Lagrangian, that is Lagrangian is not explicit function. तो हम लोगों ने बात किया था ना एक्सप्लिसिट इम्प्लिसिट की. सो नॉट एक्सप्लिसिट फंक्शन, explicit function of qk, then qk is identified as cyclic coordinate. Please, this Lagrangian is function of generalized velocity for the qk. You can see this is function of generalized velocity for the qk, but it is not explicit function of generalized coordinate. This is the beautiful part. It is generalized coordinate, but it is not explicit function. This Lagrangian is not an explicit function of generalized coordinate. Then qk is identified as cyclic coordinate. So how you will check like whether it is cyclic coordinate or not? You have to just check whether del L upon del qk is equal to 0. So what is meaning of cyclic coordinate? Why we are defining this particular cyclic coordinate? So when we are going to write the equation of motion, so what will be equation of motion? So this will be d upon dt del L upon del qk dot minus del L upon del qk is equal to 0. So if qk is cyclic coordinate, then del L upon del qk is equal to what? This value is 0 because it is cyclic coordinate. So this value is 0, which means d upon dt del L upon del qk dot must be equal to 0, which means del L upon del qk dot, which is actually generalized momentum corresponds to pk, can be identified as constant. Isn't it? Can be identified as constant. So you can see if qk is generalized coordinate, then what will happen? The generalized momentum corresponds to qk is conserved, is constant. So you can have conservation of momentum. You can also discuss conservation of momentum or angular momentum, depends on what is your generalized coordinate, what is your dimension of qk. And if it is cyclic coordinate, what is meaning of cyclic coordinate? How you will check whether it is cyclic coordinate or not? We have to check just del L upon del qk is equal to 0. You have to check for the each and every generalized coordinate. And what is meaning of generalized coordinate? How many dynamical variable must be there? How many dynamical variable must be there for the generalized coordinate?
Degree of freedom.
Exactly. So number of generalized coordinate must be equal to number of DOF. So this is our rule. And maybe the Lagrangian is the explicit function of generalized velocity, but it cannot be explicit function of generalized coordinate. Now, can it possible that Lagrangian will not explicit function of generalized velocity, but it is explicit function of coordinate?
Maybe.
Is that vice versa is true? It may be vice versa can be true. Listen, मेरे क्वेश्चन को बड़े ध्यान से सुनो. मैं ये कह रहा हूं कि कई बार ऐसा होगा कि लैग्रेंजियन जनरलाइज कोऑर्डिनेट का तो डायरेक्ट फंक्शन नहीं होगा, बट वो जनरलाइज वेलोसिटी का फंक्शन होगा. लेकिन क्या ऐसा हो सकता है कि लैग्रेंजियन जनरलाइज वेलोसिटी का डायरेक्ट फंक्शन नहीं हो, लेकिन जनरलाइज कोऑर्डिनेट का डायरेक्ट फंक्शन? डायरेक्ट मींस एक्सप्लिसिट. क्या ऐसा हो सकता है क्या?
No, sir.
नेवर ऐसा कभी भी नहीं हो सकता है. ओके, बिकॉज मे बी व्हाट इज मीनिंग ऑफ कंजर्वेशन ऑफ angular momentum means that there are not any force. बट आप मोमेंटम कैसे, अगर मोशन अगर डायनेमिक्स है तो मोमेंटम तो होगा ही होगा, जरूरी नहीं है कि जहां पर मोमेंटम हो वहां फोर्स हो ही. आर यू गेटिंग माई पॉइंट?
यस सर.
है ना? सो ये आपके दिमाग में बिल्कुल ही होना चाहिए कि लैग्रेंजियन का कौन सा फॉर्म सही फॉर्म है या फिर नहीं है. ऐसा कभी भी नहीं हो सकता है कि आप जनरलाइज वेलोसिटी नहीं हो किसी कोऑर्डिनेट का और कोऑर्डिनेट आपने यूज कर लिया हो. दिस इज अ सुपर ब्लंडर. आई विल जस्ट गिव यू एग्जाम्पल, तो उससे आप बेटर समझ पाओगे. अप टू दैट कोई डाउट है तो पूछ सकते हो. एवरीवन कंफर्टेबल अप टू दिस?
यस.
ओके. सो लैग्रेंजियन फॉर्मुलेशन में हमें यहीं तक समझना है चीजों को. नाउ वी हैव टू गो फॉर डिफरेंट टाइप ऑफ प्रॉब्लम्स, है ना? सो नेक्स्ट 3 डे we will just solve different type of problems of Lagrangian related thing. Okay, but
Sir.
before that let me ask a very basic question to you. Okay, just for the definition, nothing for the examination. Okay, so for the 3 degree of freedom, so I am giving you 3 degree of freedom. The kinetic energy is given as half m x dot square y dot square plus z dot square, and potential energy is and potential energy is half k x square plus y square. Now can it possible? क्या ये possible है? हो सकता है ऐसा?
Yes sir.
हो सकता है ना? अच्छा ये बताओ, क्या काइनेटिक एनर्जी ये हो सकता है? एंड पोटेंशियल एनर्जी हाफ के एक्स स्क्वायर प्लस वाई स्क्वायर फॉर 3 डिग्री ऑफ फ्रीडम, क्या ये पॉसिबल है?
No sir.
इट इज रॉन्ग. व्हाई? जितने नंबर ऑफ डिग्री ऑफ फ्रीडम हैं उतने नंबर ऑफ जनरलाइज कोऑर्डिनेट होने ही चाहिए. Isn't it? Now, is that this is possible? क्या ये पॉसिबल हो सकता है?
No sir.
No, it is also not possible. Why it is not possible? क्या ये पॉसिबल हो सकता है? पहले तो फंडामेंटल ठीक कर ले, है ना? क्या ये पॉसिबल हो सकता है?
Yes.
Yes,
Yes, sir.
it is possible. Okay, इसमें से क्या क्या पॉसिबल हो सकता है? Yes, this is possible. ये पॉसिबल हो सकता है? Yes, it is possible. ये पॉसिबल नहीं हो सकता है because we have 3 degree of freedom. And how do you identify degree of freedom? From the kinetic energy part or potential energy part?
Kinetic energy.
Kinetic energy part, exactly. So number of 3 degree of freedom means you need to have 3 independent velocity, isn't it? So here we have 3 independent velocity. That means it is associated to 3 degree of freedom. Don't worry about potential energy part. Potential energy has nothing to do with the degree of freedom. Nothing to do with the degree of freedom. Where is Z? Okay, Z may be cyclic coordinate, isn't it? Z may be cyclic coordinate. If I will use this kinetic energy and this potential energy as my Lagrangian, we will discuss it into next class. Don't worry. But here, it is not correct for the 3 degree of freedom because 3 degree of freedom means we need 3 independent velocity. And here, there are not 3 independent velocity. Only 2 independent velocity. This may be correct for 2 degree of freedom, but this is not correct for the 3 degree of freedom. So this is not correct. And this is absolutely wrong. Why? Because it cannot be happen that any coordinate be part of potential energy and that will not part of kinetic energy. Again, it is not satisfying. Maybe this is satisfying for 3 degree of freedom, but it is not going to satisfying for the 3 degree of freedom. So this is also wrong. And yes, 3 degree of freedom is there. Here is also this, and here is not any, maybe there is not any cyclic coordinate. So I can use this as a kinetic energy, and I can use this as a potential energy. So are you people going to comfortable up to this point?
Yes, sir.
Okay. So let's try to just recap all the definition. Okay. So I am just sticking to this one, first one. Okay. So obviously, what we have to do, first we have to find generalized coordinate, second generalized velocity, third generalized momentum, fourth cyclic coordinate, fifth equation of motion. Okay, we have to write all this thing. Okay, what are generalized coordinate? X, Y, Z. What are generalized? Is that Z is generalized coordinate? Z is not explicitly there, but it is generalized coordinate, isn't it? Why? Because Z dot is there, and we have to use the 3 degree of freedom. So Z is generalized coordinate, but it is not appeared into Lagrangian. If you will write the Lagrangian, then what is your Lagrangian here? Your Lagrangian is basically half m x dot square, y dot square, z dot square minus half k x square plus y square. So this is your Lagrangian. Generalized velocity, yes, x dot, y dot, z dot. So for the degree of freedom, the velocity part is more important. Once you have velocity part, that means they are generalized velocity. That means they are also part of generalized coordinate. What is generalized momentum here? How many generalized momentum? 2 or 3?
3.
Obviously 3, because we have 3 velocity. So first is generalized momentum related to x part. So what is this? Del L upon del x dot. This is nothing but px, and this value is nothing, mx dot. So this is for the first one. Del L upon del y dot is identified as py, that will be my dot. Del L upon del z dot is equal to m is equal to pz, that value is mz dot. Okay, let's try to figure it out. Cyclic coordinate. What is cyclic coordinate? Is that
Z.
x is cyclic coordinate?
No, Z.
No. If you can just find from here, how you know del L upon del x, the value is equal to minus kx, which is not equal to 0. So x is not cyclic coordinate. Is that y is cyclic coordinate?
No.
No. You have del L upon del y is equal to minus ky, which is also not equal to 0. So it is also not cyclic coordinate. So is that z is cyclic coordinate?
Yes, sir.
Yes. Del L upon del z is equal to 0. So that means z is cyclic coordinate. Cyclic in nature. Okay. So if z is cyclic coordinate, which quantity is conserved?
PZ.
Pz. Then obviously this quantity is going to conserve. Okay. If z is cyclic coordinate, then del L upon del z dot is going to conserve. Now we have to write equation of motion. So how many equation of motion we have to write? 3 equation of motion. Okay. So first equation of motion is d upon dt for the x generalized coordinate. Del L upon del x dot minus del L upon del x must be equal to 0. So you have to just del L upon del x dot. You have del L upon del x dot is mx dot. You will differentiate it again. Then you have mx double dot plus kx is equal to 0. Look at just like equation of motion, isn't it? mx double dot plus second order differential with the coordinates, with the time, है ना? So then this is just like a Newton's law, just like harmonic oscillator, isn't it? D upon dt, second equation of motion, del L upon del y dot minus del L upon del y is equal to 0. Again, you will get my double dot plus ky is equal to 0. Now, should I write for z coordinate equation of motion for z also?
Yes, sir.
चलो देखते हैं क्या आता है. D upon dt del L upon del z dot minus del L upon del z is equal to 0. So what is del L upon del z? 0, because it is cyclic coordinate. And from here, d upon dt, what is del L upon del z dot? Is mz dot. And from here must be equal to 0. That means mz dot must be constant. So what we will do? We have found that, okay, this is exactly same expression we are calculating from this particular cyclic coordinate. Okay, from here we can also write mz dot is constant. So for the cyclic coordinate, obviously there is not any external force, then only momentum is conserved, isn't it?
Yes.
So if there is not an external force, why to write the second order differential equation? Nothing to do with this. You will get the exactly same thing from cyclic coordinate and equation of motion for the for basically the coordinate which is cyclic coordinate. Okay, you will get the conservation of momentum. It may be angular momentum, it may be linear momentum, depends on situation. So this is basically first level of your Lagrangian formulation. So from tomorrow we will try to solve different type of problems. So tomorrow we have one another task. Why we need coordinate transformation? We will try to learn this thing exactly from this particular same problem. Okay, so let's try to wait till tomorrow. Tomorrow we will do one more basic problem, then we will go for your examination level problem. Okay. So if you have any doubt, you can just ask me.